This is the final video in our series on renewable energy sources. In this lecture, I will describe how electricity is generated using geothermal energy and what environmental constraints are faced by this type of energy generation. I will also describe how geothermal energy can be used for space heating, and I will explain the basic ways a geothermal heat pump operates and how it differs from using geothermal energy to generate electricity. The basic way that geothermal energy works is by the circulation of water into parts of the crust where there is hot rock. The hot rock heats up the water, and if we can drill down and tap into it, we can use the heated water or steam for electricity production or space heating. This graph illustrates the temperature gradient in typical surface rocks, the dashed line, and in geothermal hotspots, the solid line. Obviously, it is much easier to drill down to really hot water in a hotspot area than in typical crustal rocks. Geothermal energy is renewable, carbon-free after construction, and allows continuous energy production without having to worry about changes in weather. The energy returned on investment, or EROI, of 9 is slightly below solar power and better than tight oil, tar sands, or bioenergy sources. But because of the need for hot rocks at relatively shallow depths, geothermal energy is geographically limited, and geology controls where we can make the most use of geothermal energy for electricity production. This map indicates known geothermal regions with high energy density. Red zones are hotter than orange and yellow. Can you see the tectonic plate boundaries illustrated on this map? Look along the Pacific coastlines of North and South America, Japan, and Indonesia. You might also notice Iceland, located along the Mid-Atlantic Ridge, and zones associated with the India-Asia tectonic plate collision zone, the African-Eurasian plate boundary in southern Europe, and the ongoing rifting of the African plate. Higher rates of heat loss generally occur in areas of tectonic and volcanic activity, or where the crust is relatively thin. Superheated fluids, greater than 180 degrees Celsius, are only found near volcanic regions. This map also gives some indication of the places where geothermal energy has been developed. The US is the world leader in terms of geothermal energy generation, followed by Indonesia, the Philippines, Turkey, New Zealand, and Mexico. Iceland is synonymous with geothermal energy, drawing 100% of its electricity and 95% of its heating from geothermal plus hydropower. Here's how electricity is generated from geothermal energy. Deep wells are drilled into the rock to where they reach hot water. The hot water is then pumped to the surface, and as there is less pressure on the water when it's not deep in the rock, it converts into steam. The steam is used to spin a turbine, generating electricity. Once the steam has spun the turbine and starts to cool down, it can be pumped back in the subsurface to minimize drawdown of the water resources. In some cases, the hot rock layers might not have a lot of water in them. In that case, water is injected into the dry rocks, then pumped out, kind of like a sauna. If the hot rocks are impermeable, they can be fractured, just like in hydraulic fracturing, to enhance the water flow through them. This map shows potential geothermal energy resources in the United States, using wells thousands of feet deep and hydraulic fracturing to enhance water recovery. Darker red zones have higher potential. Black dots indicate known hydrothermal sites at the land surface. Notice how there is reasonably favorable geothermal potential in much of the western United States, but not so much in the eastern US, where the rocks are older and cooler. Besides needing the right geology, there are some additional challenges to geothermal energy production. Geothermal energy production is made challenging by the high temperatures of the rocks and water. This means that special engineering techniques and materials are needed, and that increase the costs of expanding geothermal energy production. Also, along with the steam, the wells can release hydrogen sulfide and other gases from the rocks. These can be scrubbed out rather than released into the environment. Pumping water out of the ground and allowing some to escape as steam depletes the local groundwater resources, and that can cause subsidence or sinking and small earthquakes in the area. For example, this picture shows a geothermal plant near Geysers, California, which is the largest geothermal plant complex in the world. Because of water withdrawals, the area around geysers is subsiding about 4.7 centimeters per year. If not enough water is returned to the subsurface, the geothermal field can become depleted. But injecting water can help maintain the lifetime of the resource. At the geysers, treated wastewater from Santa Rosa is injected to maintain energy production. A smaller scale use of geothermal energy is for space heating. For this, the water does not have to be as hot as for electricity generation. Hot water is piped through radiators to heat buildings and can also be used to heat pools. This photo shows a pool at the Belknap Hot Springs Resort in the Oregon Cascades. At the spring, water is 88 degrees Celsius, and it must be mixed with cooler water to bring the pool down to about 40 degrees Celsius, where it won't burn bathers. A much less geographically limited way of using the Earth's heat is through geothermal heat pumps. These pumps take advantage of stable temperatures underground relative to the air. In the winter, it's warmer underground than outside, and in the summer, it's the reverse. Basically, to provide heat, a geothermal heat pump works by circulating a mixture of water and ethanol through buried pipes. The warm ground increases the temperature of the water. Inside your home, that water can be used to heat a compressed gas. As the gas decompresses, it heats the air inside your house. The warm water can also be circulated as radiant floor heating. Once the water is cool, it returns to the pipes underground to be warmed up again. In the summer, the process works in reverse. Hot air inside your house is blown past a heat exchanger. Cold water pumped from underground inside the heat exchanger warms up, taking the heat out of the air. The warm water is then returned underground to cool off. These systems can be installed in deep wells, or they can be buried relatively near the surface if land space is available, for example, in a backyard. The systems can be expensive to install, $12,000 to $30,000 for a typical home, but once it is in place, energy usage drops 30 to 60% relative to a conventional gas furnace and air conditioning unit. And geothermal heat systems aren't just useful for homes. Kent State's architecture building has 131 geothermal wells, each 405 feet deep. This lowers the overall energy footprint of the building. To summarize what we've learned, geothermal electricity production is limited to active tectonic areas with shallow hot rocks. Where it can be used, it provides a very stable, carbon-free after construction, renewable energy source. However, the technology is expensive, and it has a lower energy return on investment than some other renewables. On the other hand, geothermal heat pumps do not require special geology. They use stable ground temperatures to heat or cool buildings, increasing energy efficiency and decreasing fossil fuel use.